All right, the objectives of today's lesson is to come to understand what we call centripetal acceleration. Centripetal acceleration. We're also going to discuss a few more attributes of uniform circular motion that we call period and frequency. All right, we'll discuss those in a minute. First off, I just want to kind of study what's happening here in my hand for a minute. All right, so let's assume that the speed in which the ball is traveling is constant. Are y'all with me? Let's assume the speed in which the ball is traveling is constant. Now, does that mean that the velocity is constant? Yes or no? Yeah, so here's the question one more time. Let's assume the speed of the ball is constant. Like it's traveling around in a circle at, say, 2 meters per second. All right, constantly. I know I'm not perfect, but let's assume that it's going perfectly 2 meters per second the entire way around. All right? Now, the question is the velocity constant? No. So I'm hearing some no's. What do you have to say, Dallas?
The instantaneous velocity is the same, but the average velocity is different.
Interesting. So the instantaneous velocity at any point should be equal to our speed, but the average velocity over what? The whole circle?
Yeah, anytime that's not instantaneous.
Yeah, it'll be different, right? Yeah, very good. So the reason why velocity is not constant is because velocity is a vector that relies on direction. So if the direction is changing, then the velocity is changing too. All right? So is the direction in which the ball moving changing when I do this? Yeah, constantly. It's constantly changing. All right? So, what do we call a constant change in velocity? We have another word for that. Acceleration. Yes. We call constant change in velocity acceleration. Yeah. We call really any change in velocity acceleration. Okay? But what we can say is that this ball is constantly changing its velocity, so that means it must have constant acceleration. Can you guys agree with that? Good. So, let me ask you a couple of questions about the direction of the velocity, all right? The leftmost point. The ball hits its leftmost point periodically, right? All right. My question to you, and I'll wait for you to answer, is what direction is the velocity of the ball when it's at its leftmost point? I see some different answers. Yes, it's perfectly downward. Perfectly downward. Now, what you said, Aiden, was that it was towards the center or to the right. That's going to be true about some attribute of this ball, but not its velocity, not at this point. Okay? Now, what about when it's at its bottom point? Perfectly horizontal to the right. All right? Let's investigate 2 more points. What about when it's at its rightmost point? Yep, y'all got it. Perfectly vertical, upwards. All right, and then one more. Top point. Perfectly to the left. All right? All right. And then let's say that we set up a normal XY axis where the origin was at my hand. All right? Then the Y axis goes up and down and the X axis goes horizontal. All right? Those are the only 4 points in which the direction of velocity is perfectly parallel to one of the axes. Do you agree? And then for all the other points, it's changing in between. All right? Good. So I'm just doing this so that we can establish some kind of visual for what's actually happening here. What we're talking about when we have uniform circular motion, because it's going to be the same every time. And so if it's going to be the same every time, then we can set up some equations that will help us to find certain attributes of the uniform circular motion. All right, here's my next question. If it's accelerating, what direction must the acceleration be? We're going to actually talk about this one in a little bit more depth, but I am looking for some maybe educated guesses here. Go ahead. Towards the center? Towards the center would be correct. All right? We're going to discuss a little bit more deeply about why it's towards the center. All right. Everybody remember early in this course when we discussed vector addition and vector subtraction? Remember when we did it graphically? I'm going to ask you to recall how that kind of looks so that you can understand the reasoning behind what we're going to discuss in this lesson. Okay? Take a look at this picture. We have kind of a snapshot of an arc, a portion of uniform circular motion, where that point at the bottom might be my hand, okay? And then the radius labeled lowercase r would be the length of the string connecting my hand to the ball. Okay? So could be the length of the string connecting my hand to the ball. All right? And then the ball would be at point A there. So let's imagine that point A on the screen is the topmost point in the ball's circular path. In this case, the velocity, as you can see there, should be perfectly horizontal. But as the ball continues a little bit further along its path, the velocity changes direction a little bit. Everybody can see this? So let's just arbitrarily take some point a little bit past that topmost point and call it B. All right? If we measured the direction of the velocity at point B, then we can see that it is not perfectly horizontal or vertical. It's just changed direction a little bit in between. And so what I'm going to try to remind you of here is that over the course of this space, the ball is accelerating in some direction, which is what's causing the direction of the velocity to change. Do you agree with that statement? Okay, so over this period, there is some average acceleration. Right? Does anybody remember and can remind me of what our definition of average acceleration is? Exactly. Our definition of average acceleration is change in velocity, which is a vector, by the way, over change in time. This is important. This is important because it's kind of the same thing as 1 over change in time times change in velocity. Did I blow anybody's mind with this? Hopefully we're all good enough at algebra where something like this doesn't scare you. Okay? Why did I do this? Well, I did this so that I can illustrate for you that what's happening here is just a scalar multiple. Do we remember that term? Scalar multiple from earlier on in this course. What happens when we have a scalar multiple is we're multiplying some scalar by some vector. And one of the key things to remember about a scalar multiple is that the direction of the vector does not change, only the magnitude. So if I can figure out what the direction of my change in velocity is, then I can know what the direction of my average acceleration is. Because we're taking a scalar multiple here, so whatever direction the change in velocity is will be equal to the direction of my acceleration. And that's going to help me to make a couple of statements about physics a little bit afterwards, but I need you to understand why it's true. That's why we're doing this. Okay? So that's really fun because now that I know all I need to do is find the direction of my change in velocity, then I can take my first velocity vector, and I can find the difference between my first velocity vector and my second velocity vector. This is just vector subtraction graphically, okay? If I just take some vector subtraction graphically, notice that this vector corresponds to vector 1, and this vector corresponds to vector 2, and if I put them together to take a graphic vector subtraction, then I'm going to have this vector, which I can now call delta v because it's the difference between my two vectors. Does that make sense to everybody? Okay. So I've graphically done some vector subtraction here, and what I got was some resultant vector delta v that points in the direction that you see on the screen. If I take that and place it in between my 2 points, I can see that resultant vector is pointing towards the center of my circle. So then that must mean that the direction of my acceleration, based off of the argument that I made here, must be towards the center of my circular path. We can test this 1,000 different ways with 1,000 different changes in position on the circular path. You're always going to get a change in velocity that points towards the center, okay? And if we make this displacement smaller and smaller, entering the realm of calculus, then what you're going to see is that at any instantaneous point on the circular path, that the direction of the acceleration is along the attached string towards the center of the circular motion. Does that make sense to you guys? And then just to test it to see if that's a reasonable conclusion, we can just take a look at our setup. What's causing the ball to not fly off into space? The string. So tension force due to the string is causing the ball to change direction, all right? Well, tension force always goes along the string that the ball is connected to. So that, that natural understanding of physics corroborates our mathematics here on the screen. So the point is that we now know that when an object is in uniform circular motion, it has acceleration that points towards the center of that circular motion. We call this acceleration centripetal acceleration. We call this acceleration centripetal acceleration. Centripetal just means pointing towards the center. It's a Greek word. Center pointing, all right? If the acceleration, and here's a little side note, guys, it's not necessary for today's lesson, but it will be necessary for the next lesson. If acceleration is centripetal, meaning that if the acceleration is pointing towards the center, what direction must the net force on the object be? Also centripetal, okay? So I'm just hinting on that fact so that you can see and understand in the next lesson. Also, Newton's second law still applies here, okay? So if we have centripetal acceleration in the mass, then we know what the centripetal force is, okay? Now, that said, here is some steps on a proof to come to some equation that will allow us to calculate centripetal acceleration when we have uniform circular motion. All right, I'm gonna request that you walk through those steps on your own as the notes are attached. But for today, so that I don't confuse you and I don't put you to sleep, let's just discuss the result. The result is that if we have an object in uniform circular motion, then that object has centripetal acceleration equal to its velocity squared divided by the radius of its circular motion. Okay? Remember, uniform circular motion assumes constant speed throughout its path. So that velocity is really just the magnitude of its velocity. We're not concerned with what direction it's facing at any specific point. Make sure we get this down. This is really the first main character of Unit 5, guys. Yes? A sub r is centripetal acceleration. So now that we've established that the acceleration vector on an object in uniform circular motion points towards the center of a circle, we can say that the velocity vector always points in the direction of motion, which, as you can see from this image, is always going to be tangential to the circular path, okay? What that means here, guys, just some quick conclusion that we can make is that if this is the case, and this is true for uniform circular motion, then the velocity vector and the acceleration vector are always going to be perpendicular. They're always going to be perpendicular. This helps with some of our trigonometry down the road, okay? One last little tidbit, guys. Circular motion, when we're talking about the motion itself, is often described in terms of frequency, typically denoted by a lowercase f, and period, typically denoted by a capital T. All right? Frequency is the number of revolutions per second. In other words, how many times this ball will make a complete revolution per second. Okay? Period is just the inverse of frequency. Okay? Period is the number of seconds per revolution. Okay? How many seconds it takes for the ball to make one revolution. If you have frequency, then if you just take 1 over frequency, you can have the period. If you have period, and if you just take 1 over the period, you have frequency. This is going to be very important. This is going to be very important for finding the velocity of our object. Okay? So, just to elaborate, for frequency, we have revolutions per second. But for period, we have seconds per every revolution. They're just inverses, okay? This is a true equation. Now, I want us to consider something. We're talking about velocity and magnitude of velocity on the circular path. Oh, sorry. But in reality, the instantaneous velocity is equal to the speed at any point on this path. We discussed this a little bit earlier, right? So, I'm going to ask you one more relationship. I'm going to ask you for one more relationship which we've discussed earlier in this course. It's the relationship for average speed. Can somebody tell me what it is? Yes, it's equal to total distance over time. Now, this is a very important relationship because we can use period and frequency to find the velocity an object is traveling when it's in uniform circular motion. Okay? If we take the total distance to be the circumference of the circular path, and we take the time to be the period it takes to make one complete revolution, then we can very easily get meters per second, which is going to be equal to our object's speed and the instantaneous velocity of our object at any point, or the magnitude of instantaneous velocity at any point. Once we have that, if we know the radius of our circular motion, then we have everything we need to solve for centripetal acceleration, which of course, as a reminder, is equal to v squared over r. Today's not really about dynamics, but I do want to mention one last thing. Don't forget that Newton's second law still applies here. So F centripetal is still going to be equal to ma if we're using centripetal acceleration. All right, keep that in mind, guys, because we're going to call to that idea in some of the practice problems for this set. Are there any questions?